So yes, I'm a research associate at the Institute of Particle Process Engineering, and I work on a joint project with the Institute for Occupational Safety and Health, so the German Social Accident Insurance. So therefore today I will present the result of the ongoing project on behalf of the IFA Institute. So the sampling to determine dust exposure in workplaces is always actively conducted by means of sampling. So they're attached to the workers' clothing in the prison zone, and they're used to assess the individual's exposure to the occupational airborne dust. For the respirable dust fraction, the most common are cyclone samplers. So they consist of cyclone precipitator and a filter cassette mounted on her side. So the small fraction means respirable fraction, particles small enough to penetrate to the alveoli, to the gas exchange region, are collected on the filter, and larger particles are separated in a cycle and collected into the grid core. So, according to the respirable convention determined by EN 481, all respirable samplers should provide the following sampling efficiency curve with a cut size of 4 micrometers aerodynamic diameter. So nowadays there is a wide range of the samplers available on the market. So they all operate at a flow rate from 1 up to 10 liters per minute. So, however, in some cases the sample duration is rather long, since it requires some time to collect the required mass of particles on the filter for the further accurate gravimetric analysis. So also the limit values have been always decreasing, so and will be decreasing in the future. So therefore there is a need in samplers which can operate at larger flow rate and are able to collect the required mass on the filter for further gravimetric analysis. So therefore the main objective of this project is to develop a respirable sampler for a flow rate which is twice larger than available on the market, so for 20 liters per minute. So based on the available cyclone samplers, 3 cyclones were designed, namely the HD design, which was originally developed by Higgins and Yule almost 70 years ago, Gussman and Kenny design, and also Uniflow cyclone, which was used as a precipitator in the SPG P3 3-stage aerosol sampler, which was developed by the Federal Institute of Occupational Safety and Health in Germany, Bauer. So the HD design is used, for example, in different samplers as FSP2, FSP10, Simpex, Casella, and other GK, for example, the GK4162 and others. So for 20 flow rate, the HD cyclone has diameter of 3.25 centimeters, so it was named as HD 325. And correspondingly, the GK cyclone has diameter of 6.27 centimeter, and the Uniflow cyclone has diameter of 2 centimeters. So, and these cyclones were investigated computationally using CFD simulation. So, with some physics behind the CFD simulations. So, for accurate prediction of the swimming flow in the cyclone, the larger simulations were applied. For that, the 4 filtered Navier-Stokes equations were solved in order to model turbulent subgrid scale stresses were modeled using a Busniewski assumption, and dynamic Smagorinsky model was applied to predict the subgrid scale viscosity. So then the particles were tracked through the simulated flow field. So and tracking was performed by forming a set of differential equations in time for particle position and particle velocity. So the most important forces which act on the particles are the drag force and the net force due to the gravity. So therefore these forces were taken into account when modeling particle behavior. So, and the drag coefficient was calculated according to the Schiller normal correlation, but modified by the Cubian conversion factor. So, since samples separated really low particle concentration, the effect of particles on the flow field was neglected. So, the CFD model was validated by comparing the pressure drop and penetration of the FSP2 and FSP10 samples. As one can see, the deviation between the simulated pressure drop and simulated penetration curve for both cyclones are below 10%. So we can assume that the used CFD model can accurately predict the performance of the sampler. So the flow field in these three designs was investigated. So as one can see, for example, in the HD cyclone, not the whole volume of the cyclone is used for particle separation. The water doesn't penetrate deep into the grid pore, but instead attaches to the cold wall and rotates. So, and below this point, the velocity are close to zero. So there is like a dead zone beyond this point. So, and the similar flow pattern was found in a smaller HD design, in FSP2 and also in FSP10. In contrast to the HD design, the vortex in the GK cyclone and the uniflow cyclone penetrates deep into the grid pore and ends on the bottom. So, due to the lower cyclone diameter, the velocities in the uniflow cyclone are higher. And as a result, one can see the lowest pressure drop in the larger in size GK cyclone, and in HD cyclone they're 25% larger, and in the uniflow cyclone they're by 3.5 times larger than in the GK cyclone. After that, the particle penetration was through this cycle was analyzed. As one can see, almost all three cyclones provide a cut size approximately 4 micrometers. However, for larger particles, meaning particles larger than 5 micrometers in size, there is significant deviation compared to the respirable convention for the HD design and the uniflow cyclone. The GK design follows better the respirable convention. So therefore, this cyclone was selected as the most preferable. It was manufactured in metal version at the IFA Institute and tested. So for experimental measurements, the compressor was attached to the cyclone. So this sampler was tested at both institute, at the MFO Institute and also IFA, you can see here. So, and the results uploaded in this figure. One can see that both measurements showed slightly reduced penetration with a lower cut size, which is 3.45 and 373 micrometers compared to respirable convention, which is 4 micrometers. So, and this is smaller than the previous simulation, which showed that it should be close to 392. So, therefore, the cyclone was additionally simulated with a compressor. So, and what we have seen that the compressor reduced the penetration. One can see that the simulated penetration agree well with both experimental data. Probably for smaller particles, the result fit better to the measurement at the MFO Institute, and for larger particles, measurement with the IFA. So, the compressor installed downstream of the cyclone reduced the particle penetration. So, to analyze why it happens, so the particle deposition on the walls were calculated, and so one can see that a significant amount of particles collected on the compressor wall. And also after the test, a thin layer of the particle deposited on the compressor wall was observed. So why does it happen? The flow exiting the cyclone is still swirling. So therefore, during the contraction of the flow, this cone confessor operates as an inverted conical cyclone. So therefore, the particles are separated here due to the centrifugal forces. So if one calculates the penetration, let's say, upstream of the confessor and downstream of the confessor, one can see that there is a large particle losses in the confessor. But nevertheless, the cut size is still lower than 4 micrometers. So one can look deeper into the flow field inside the cyclone sampler. So one can see that the confessor affects the flow field not only in the vortex fine, its outlet part, but also in the inner region of the in the cyclone. This region is more pronounced and highlighted in yellow color. So it can be better seen when one plot the tangential and axial velocity at the cut plane corresponding to the intersection of the cylinder and conical part. So one can see the confessor or tangential velocity are higher. So as a result, the particle exert a stronger centrifugal force field, and therefore they are collected with a higher efficiency. So therefore the confessor reduces the penetration based on two mechanisms: particle losses in the confessor and also higher tangential velocity. So to reduce these particle losses and diminish this effect, a four-way flow splitter was developed. For test, this flow splitter has the same diameter at the outlet of the cyclone, so it's assumed that it shouldn't affect the flow field in the cyclone. And additionally, the cyclone with the filter cassette was simulated, which is supposed to be used in real applications. So the filter was modeled as a porous media, and the permeability and pressure resistant coefficients were determined from experimental measurements. So as one can see, that the flow field in the cyclone, either with the developed four-way flow splitter or the filter cassette, is absolutely the same. So the downstream configuration doesn't affect the flow field in the cyclone. So we assume that the test with the four-way flow splitter, which is needed for aerosol sampling measurements, should provide corresponding or the same result as the sampler with the filter cassette, which will be used in real applications. So the GK sampler with the four-way splitter was tested at the Institute using two aerodynamic particle sizes, one from our institute, another from the IFA Institute. So using the full experimental setup. So the different test darts were dispersed with a PEROSH disperser, RBG 1000, and were generated into the aerosol box, to which the sampler was connected. On the way to the aerosol box, the aerosol was neutralized. Downstream of the cyclone, the flow, 20 liters per minute, was split equally into 4 flows, each one 5 liters per minute. 2 of them were used for downstream sampling, and 2 others were matched together and drove through the filter the vacuum pump. So, and the penetration counts were calculated based on the measurement of these 2 sampling devices, one from IFA and one from FOT. So here you can see the penetration kept measured with 3 different test darts: micropel, spherical glass bead, and 2 Blatini glass beads, 2400, 2429. So the measurements were performed at mean aerosol concentration up to 145 milligram per cubic meter. So all results show that the cut size is close to 4 micrometers. However, the APS from IFA showed a bit high deviation. So in this plot you can see the dots represent the mean penetration, the error bars show the minimum and maximum values, and the shaded area showed the ±1 standard deviation. So when one analyzed the whole all measured data and plot here them as mean value and standard deviation, and using the approximation or approximating the result with the Gompers function, one can determine the bias map of the sampler according to the EN13205. So as one can see, the bias in the sample concentration is below 8% for all 216 aerosol size distributions of interest which are determined by this standard. So the developed GK sampler conformed to the Spiral Convention and also to the requirements mentioned by the EN13205. So the following conclusions with different designs were analyzed. It's important the downstream configuration plays a significant role in particle sampling. So the four-way flow splitter was developed to minimize particle losses during sampling, and the developed GK sampler for a flow rate of 20 liters per minute conformed to the respirable convention and has a bias below 8% for all 216 aerosol size distribution of interest. So this project is still going on. The next step is further optimization of the sampler, namely reducing the size, the mass of the sample to make it more wearable. So, and the two new prototypes have already been investigated. One with diameter 4.5 centimeters, and another with 2.5, and now they are in the manufacturing phase, and further will be tested. Thank you very much for your attention.